Just like with derivatives, anytime we have pieces that are separated by addition or subtraction, we can think about each of those pieces as sort of its own separate problem. Looking at x to the 2/3, since I have x raised to a power, I can add 1 to that exponent and divide by the new exponent. Oh, I didn't add 1 to the exponent. Oops. Okay, we'll just add 1 and say 2/3 plus 1. Added 1 to the exponent divided by the new exponent. The nice thing about taking this class online is, well, I guess it wouldn't even matter, but since you're turning in that written homework, if fractions are not your friend, at least you can use a calculator to make sure you got it right. Okay, that next piece, because we're separated by a plus, I still have a number times x raised to a power. When I integrate that or find that antiderivative, we're going to add 1 to the exponent and divide by that new exponent. Looking at negative cosine, it's not an x raised to a power. We've got a trig problem, so I'm thinking about whose derivative is equal to negative cosine. And the function whose derivative is negative cosine, negative sine. And over here, that 3 is just chilling out in front. 3 is coming along for the ride. And the function whose derivative is e to the x is e to the x. And my plus c is kind of floating off in space here, so let me bring it up here. I know that I mentioned this on Wednesday, but page 345 of our textbook has a box with the basically generic antiderivative rules. You really should memorize those. Every single one of those derivative rules that's in the box. Chances are you've already got a couple of them memorized just from working through some homework problems, but make sure you take a look at the entire list. Dx. I'm going to walk up to this integral and I'm going to say, okay, it's just algebra. I wonder if I can make it look like x is raised to powers. And well, kind of. I can take that square root and I can rewrite that square root to say 4 plus x squared raised to the 1/2 power. The problem is I can't sort of distribute in that 1/2 power. There isn't anything that I can do to simplify the square root of 4 plus x squared because of that addition sign. I'm not going to be able to do anything to that. So my next line of defense in terms of integration techniques is to say, does the derivative of one part equal another part of the problem? And the answer is, well, kind of almost. I'm going to come off to the side and build my vocabulary list. So thinking about this, thinking about that u substitution, sometimes u stands for ugly. What's the ugliest part of the problem? Or what's the messiest part of the problem? Well, really, we can probably all agree that the messiest part is that square root thing. I'm going to let u equal all of that stuff inside of the square root. There is more than one way to work through this problem. I'm going to show you my favorite way to work through the problem. I am building a vocabulary list over here, and I have to translate everything in this problem based on my vocabulary list. Right now I have a u and something with an x, but I know that I'm going to have to translate this dx piece, so I have to take a derivative. If I find du dx, so I'm taking a derivative here, the derivative of 4 is 0, and the derivative of x squared is 2x. This, I'm now going to multiply both sides by dx, so that I have du is equal to 2x dx. And the truth is, I don't usually write this step out. I'm writing it out because we're sort of just getting started with u substitutions, but I don't write this step out. I can save myself the time by just going straight from here to here. Thinking about this as a vocabulary list, I don't have 2x dx in my problem. but I do have x dx. So my choice of how to deal with that is to take this, divide both sides by 2, and say that 1/2 du is equal to x dx. Now, I have two things that I can substitute in the problem to convert this entire integral into a question in terms of x's to a question in terms of u's. So that x dx becomes 1/2 du. And the 4 plus x squared, I'm going to replace with u. And that is still raised to the 1/2 power. Just like when we're dealing with Riemann sums, don't worry, I won't say that word very often. I know that when we have a constant inside of a sum, we can pull that out in front. Well, the same thing works here with integrals. So that 1/2 I can choose to take out in front of the integral and write this as 1/2 integral of u to the 1/2 du. From doing this, now I have a u raised to a power. This we know how to do. I'm going to add 1 to the exponent, divide by the new exponent. So I've got 1/2 u. When I add 1 to 1/2, I get 3/2, and then I'm dividing by 3/2 plus a constant. And our last step when we're doing these u substitutions for indefinite integrals is that I've got to translate everything back into x's. I'm going to go ahead and simplify those fractions really quick first. Dividing by 3/2 is the same as multiplying by 2/3. So when I flip that over to multiply, the 2's will cancel, and this fraction will become 1/3. So this turns into 1/3 of, and substituting our u back in, I've got 4 plus x squared, all to the 3/2 power plus a constant. And that's going to be my final answer on this. I've got 1 plus x squared divided by 3x plus x cubed dx. I'm going to walk up to this question and say, well, it's just algebra. Is there a way that I can make this look like x's raised to powers? And the answer is it kind of already has x's raised to powers, but I have division going on in this problem. And we do not have an integration rule like comparable to the quotient rule. So instead, I'm going to look at that and say, I wonder if the derivative of one part is equal to the other part. And when you're first starting off doing u substitutions, you might have to just write out the parts and check the derivatives. So we have two parts here. I've got the top and the bottom. So let's just check. If I were to let u equal 1 plus x squared, then du would be 2x dx. And that wouldn't really give me a way to do anything with the denominator. So this probably isn't a good choice. Well, let's make the other choice. What if we let the denominator equal u? If u is equal to 3x plus x cubed, then du is 3 plus 3x squared dx. Well, gosh, that's almost what we have on the top. Since it's almost what we have on the top, I'm going to manipulate my vocabulary list so that it's exactly what we have on the top. And I'm going to do that by factoring out a 3. When I make the substitution now, I don't have 3 times 1 plus x squared dx. I just have the 1 plus x squared dx part. So I'm going to divide both sides here by 3. when I go to substitute out the 1 plus x squared dx, I can swap that out for 1/3 du. And then my denominator, 3x plus x cubed, that's what I called u. It is a choice, but one choice is to push that 1/3 out in front and then be left with 1/u du. And then we look at that and say, oh wait, whose derivative is that?
This becomes deprotonate. And then just a little bit more equivalence, one full equivalent, and a little bit more.
Somebody's watching other fun stuff. That's cool.
pH changes.
But I am gonna mute you. Someone's watching other fun videos. Okay. Someone muted themselves. Thank you. Back to here. I've got that 1/3 times 1/u du. Looking at that, whose derivative is that? Well, that's the derivative of natural log. So I'm going to write 1/3 natural log. And I'm going to remember to put that absolute value on there so that our domain of 1/x matches the domain for the function after we've integrated. Final step, we wrote it in u's. I've got to turn this back into x's. So I've got 1/3 ln u was right here. So that's 3x plus x cubed plus a constant. Here are a couple of u substitutions that tend to hide. I walk up to this problem. I'm going to look at this problem, say, gosh, it's a mixture of stuff. I've got some exponential stuff. I've got some algebra stuff. I sure hope the derivative of one part is equal to the other part. Well, if U stands for ugly in a problem, and I'm looking at this problem, the square roots are kind of the thing that's making it ugly. Let's just see what happens if U were equal to the square root of x. Since you all were not hanging out with me for 17a, I'm not sure how you memorized the derivative of the square root of x. Personally, if y is equal to the square root of x, I've memorized that y prime is 1/2 root x. Alternately, I can think about that square root of x and rewrite it as x to the 1/2 power, so that when I take that derivative, I get 1/2 x to the negative 1/2 power dx. If this is how you've memorized finding the derivative of the square root of x, then this problem is a little bit sneaky. Because once we've got this derivative, we really need to rewrite that so that we can see that the x to the negative 1/2 power is a 1 over the square root of x. Because that's what we have over here that we're going to make that substitution with. So I have the 1 over square root of x and the dx part. What I don't have is the 1/2. So again, I'm going to manipulate my vocabulary list so that this says 2 du is equal to 1 over the square root of x dx. Now I can push this back over here and translate all the pieces so that I end up with e to the u times 2 du. Again, it's a choice. You can move that 2 out in front of the integral. You don't need to. If you chose to, you could. And the function whose derivative is e to the u is e to the u. So we get 2 e to the u plus a constant. And always remembering that since the question for this indefinite integral was asked in terms of x, I need to make sure to give my answer in terms of x. As a very similar sort of problem, or rather with a similarly sneaky u-substitution, if I had something like e to the negative, how about e x to the negative fourth divided by x to the fifth. Similar to what happened with that square root over there, here, it may not be immediately obvious the answer to that question of does the derivative of one part also appear in the problem? And if I let u equal x to the negative fourth, then when we take that derivative, we get negative 4x to the negative fifth dx. And we can rewrite that to say negative 4 over x to the fifth. And I have that dx over x to the fifth part. The only thing I don't have is the negative 4. So building that vocabulary list, I'd have negative 1/4 du is equal to 1 over x to the fifth dx. And I'll give you just a minute to try finishing that up on your own. To make that u-substitution and then evaluate the integral and then bring it back around to be in terms of x. How'd I do? Did I get what you got? I'm going to walk up to this integral and say, hey, it's just algebra. Can I make that look like x's raised to powers? And the answer to that question is yes, absolutely. We can multiply this out. We can make this 3x times 4 minus x squared times 4 minus x squared times 4 minus x squared and FOIL all that garbage out. But that sounds like a lot of work. So instead, I'm going to think to myself, I wonder if I can do a u-substitution. Does the derivative of one part, kind of, sort of, equal another part of the problem? If I have to choose between these pieces, in terms of what I'm going to let u equal, I'm going to choose the part that's a little more complicated. That's going to be this 4 minus x squared piece. And if u is equal to 4 minus x squared, oh, I really did this wrong. Oh, well, we're good, we're good. It's just not the first example I wanted to do. So if u equals 4 minus x squared, then du is going to be negative 2x dx. Well, I don't have the negative 2x dx part in the problem, but I do have an x and a dx. So the piece I don't have is that negative 2. I'm going to divide both sides by negative 2 so that my vocabulary list has what I need. I can go about correcting, translating the problem now. That 3, since it's a constant, I can pull out in front of the integral. And the x dx part became negative 1/2 du. And this whole part became u cubed. There's an extra piece to translate this time. And the other piece that I need to translate now are these limits. Secretly, when we write a definite integral, whatever the variable of interest is, in this case it's ex, that's what this 1 and 10 are equal to. This is really an x equals 1 and an x equals 10. And that's going back to this idea of that definite integral representing an area under a curve. So these are like the x values that you're going from 1 to 10. That means that when I make my vocabulary list over here, I also have to translate those values. And I'll squeeze it in here, sure. So we've got x values and we need to turn them into u values. And when x is 10, when I plug that in here, 10 squared is 100, 4 minus 100, negative 96. And when x equals 1, and I plug that in here, I've got 4 minus 1 squared, and I get 3. Well, the important thing to note is that when we're making these substitutions, and I'm changing these limits of integration, they have to match up in the same location where the x values were. So that 10 was on the top, which means my negative 96 goes on the top. And that 1 was at the bottom, which means the 3 goes on the bottom. And if that is feeling totally wrong to you, it's mathematically correct and also unsettling, because generally we want that smaller number to be at the bottom and the larger number to be at the top. I am not ignoring the question in the chat. I'm getting there right now. And the question in the chat is, what became u cubed? So looking in this problem, the 4 minus x squared is what I let equal to u. And since that equals u, this was u cubed when we do that translation. So hold on tight with the fact that the number furthest to the left on the number line is at the top. That negative 1/2 I can pop out in front to make this negative 3/2, 3 to negative 96, u cubed du. And here is where I'm going to deal with that minus sign. You don't have to deal with it at this moment, but I'm going to choose to deal with it at this moment. One of our rules in terms of definite integrals is that if I want to switch this order, then my entire integral becomes negative. Meaning I can swap this around and actually say that's negative 96 to 3, but I'll change the sign of the integral. Now the cool thing, or one convenient thing, when we are doing a substitution on a definite integral is we never have to take this back in terms of x. Because we've made this substitution and we made the substitution on the endpoints, when we finish the integral, we're going to get a number. So we're totally done. There's nothing extra to do. So now I'm applying that fundamental theorem of calculus piece that says I need to find the antiderivative of u cubed. And that is going to look like add 1 to the exponent, divide by the new exponent. So I have that 3/2. I'm going to add 1 to the exponent and divide by the new exponent. Notation-wise, we're going to put a vertical line to show that we are about to evaluate it at 3 and 96. Just because I don't want that to look like a 24, I want to remind myself that there was really multiplication going on there. So if I wanted to simplify that, that's 3/8, or 3u to the 4th over 8. I'm going to plug in that 3 first, so that I've got 3 times 3 to the 4th over 8, and subtract off, plugging in the 96. Sorry, negative 96. 3 times negative 96, whole thing to the 4th, over 8. And then I'm just going to walk away. I have no idea what 96 to the 4th is. That's what I meant when I wrote the problem. And then I was like, oh, I didn't really need to do that. I didn't, because I didn't want to deal with a number that big. But